Well, Lewis structures continue for another day, and with that, what we need to discuss is this concept that I introduced of resonance. And well, we have an example of ozone, the Lewis structure for ozone drawn here. And the thing about ozone is when you do the Lewis structure for it, to balance it out, you end up getting um, a double bond and a single bond. And then all the octet is taken care of. But the problem is, so this works on paper, but the reality is when we look at it, when we actually observe ozone, the molecule, both the oxygen bonds have the same length. That means the nuclei of the oxygens are the same distance from each other. So what that means is if there had been a one bond of oxygen is double and bond is a single, then we would expect to see two different lengths, but we don't see that. And so what happens, so what we need to say is that, in a sense, both of the outer oxygens have a minus half charge rather than one having a plus and one having a minus when it comes to their formal charge. And so you could actually draw two different structures because there's three oxygens and you would have two basically mirror images of each other. And so what we're saying is that the Lewis structure, although follows the octet rule, it doesn't model what the structure actually is. So we use multiple structures to indicate that there isn't just one structure that best describes it. So we have what are called resonance structures that describe the molecule. And just as green is a synthesis of blue and yellow, ozone is a synthesis of the two resonance structures. So technically the ozone molecule isn't one or the other, it's both. And the collected data supports that in the fact that the distance of the two bonds between the oxygens are the same distance, and they're not quite as long as a single bond, and they aren't quite as short as a double bond. So it's kind of this in-between length. So in truth, the electrons that form the second CO bond in the double bonds below do not always sit between the carbon or the oxygen. Okay, we're back. Where did I leave off? Okay, so in truth, the electrons that form the second carbon-oxygen bond in the double bond below do not always sit between the carbon and that oxygen, but rather can move among the two oxygens and the carbon. So what is said, kind of the electrons are said to be delocalized, meaning they aren't restricted between just one carbon and one oxygen. They move around, they float a bit. Okay, and so what that means is that when we look at the length or the distance of those carbon-oxygen bonds, we don't see one single oxygen bond and one double oxygen bond, but we end up seeing a hybrid of bond lengths that are identical between both carbon and oxygen bonds. So they are not localized, they are delocalized electrons. Okay, so double bonds are really common in organic compounds, and here's an example of a resonance structure. So this is benzene, and benzene is C6H6. It's a ring structure. There are three double bonds, but you can draw the Lewis structure these two ways. And in reality, there isn't, when you look at the bond lengths of the carbons within the ring, they are all the same length. So you don't have singles and doubles, you have hybrid because you have this resonance structure. So you have these delocalized electrons that make the structure the way that it is. And so, and then on the bottom, there's several other ways to draw it with using organic nomenclature. So typically we just depict it with a hexagon with a circle inside because you have a lot of delocalized electrons in that ring that make it function. And benzene and a lot of aromatic rings have kind of these delocalized electrons. All right, so that's it with resonance, and we will work on this stuff in class. See you then.